Howdy, howdy, howdy. Welcome back, my friends. Whoops. So here we are in our third lesson of Unit 8. So we are going to work on our real life applications of these growth and decay models for exponential functions. So 8.2 is where we really got a lot of the algebra and solving. And so now we're just going to take that algebra and apply it to a word problem. And kind of talk about different scenarios where these exponential functions occur in our everyday life. And so depending on that, we have to set them up just a little bit differently. So here we are with our first example. Notice I just start off the bat with those exponential growth and decay models that you already saw in last lesson. So some initial value, A, which is the same thing as a vertical stretch or compression, but it's the initial value times 1 plus the rate. And remember, the rate is always going to be represented in the problem as a decimal, but we say it's growing or decaying at a rate in a percent. So if we see something like 1 plus 0.079 or something like that, we would know that this is growth and it's growing at a 7.9% rate. Okay, we talked about that in the last class. So first example, it says the value of a car in thousands of dollars can be approximated by the model y equals 31 times 0.92 raised to the t power, where t is the number of years since the car was new. First thing is we want to know is whether this model represents exponential growth or decay. So to tell that, we look at our base. Our base is a number less than 1, so therefore this is showing decay, which makes sense because that's what it is in real life. When you buy a new car, it depreciates over time. It actually depreciates the minute you leave the parking lot of the car dealership. So this is decay. So then it says, identify the annual percent increase or decrease of the value of the car. Well, here's where we can take our initial model that's given to us and rewrite it in the form that we want. Y equals our initial amount, which is still 31, times, we know this is decay, so we're going to write it as 1 minus 0.08 raised to the t power. And so now that it's in this model, we know exactly how much it's decreasing by, because we already know it's decay, and it's decreasing by 8%. Okay, so every year that since the car is brand new, it's going to decrease or depreciate by 8% of its worth. Then it says, estimate when the value of the car will be $9,600. Well, let's kind of pick apart what this problem is giving us. Because our initial amount is the 31, and this problem says we're putting everything in thousands of dollars, this brand new car was worth $31,000. Every year that you have it, it depreciates 8%. So how many years is it going to give us a value of $9,600? Well, that's our y value. So I'm going to set up my equation as 9.6 equals 31 times 1 minus 0.08 to the t power. That's what we're trying to figure out. The reason why I put 9.6 again is because we're writing it in terms of thousands. So this is 9,600, so 9.6. We actually do not have the algebra to solve this right now. That's the second part of our unit, which is using logarithms. So we can't solve this right now, but algebraically, but we can solve it by graphing. So by graphing, we can see what that t value is going to be. Now, here's where I'm going to kind of pause and talk to you about graphing. If you have a handheld Casio, you should be able to plug this into your calculator, this formula, okay? And what you're going to do on your calculator, if you have a Casio, is you're going to calculate, and you can actually do like a G-solve, I believe. So you can calculate or G-solve, and you're going to want an X calculation. The reason why you want an X calculation is because you know the value of y. You want to know what is the X value when y is 9.6. Okay, so if you go to G-solve or calculate or whatever it is, and you go to X calculation, it's going to ask you, what's the Y value? You will enter 9.6, and then it will show you that exact point on your graph, which is about 14 years. If you do not have a physical calculator at all, here's where I'm going to recommend that you download that VM Horizon software if you haven't already on your iPad. There is a video on how to do that in the course information folder on Schoology. Or if you're familiar with another online calculator that can do these skills, you're more than welcome to use that. If you have a handheld calculator but it's not Casio, possibly it would be a TI, you can also solve this on the TI by graphing. But what you'll do a little bit differently on the TI is you'll input this formula again, okay, into one of your y equals, and then the other y equals, you're going to enter your 9.6. So that means on your graph, you're going to get the exponential of what we have. Actually, sorry, it was showing decay, so it would look something like this. And then you'll get the horizontal line of 9.6, and where they intersect is going to be your answer. That's obviously not a great model because we already know that. So maybe it's like something like this, and that would be 14 point something, comma 9.6. So you can just find where those two graphs intersect, and that's your answer. Okay. All right, and so you're gonna kind of use that method of solving in another question further along. So again, if you have the Casio, you can G-solve. If you have a TI, you can find the intersection. If not, use an online calculator. All right, next problem. In 2000, the population of the city was about 1.04 million. During the next 14 years, the population increased by 2.05% each year. We want to write an exponential growth model given the population y in millions t years after 2000. So we know that it's growth because it says that the population is increasing by 2.05% each year. So we already knew it was growth. Okay, if you need to still see your growth models up here, we're going to mimic this one right here, growth. So y equals. Now remember, we're writing this in terms of millions. What is your initial amount? Your initial amount was 1.04 million times growth. 1 plus what is your rate? Your rate is 2.05%. So writing that as a decimal, moving your decimal 2 places to the left, you're going to get 0.0205. And then, of course, that is raised to the t power, which is representing the years after 2000. So this is the model that we're using for this specific problem. The first question is asking, what is the city's population in 2008? So I am solving for a y value, and that means my t value is going to be how many years after 2000? Well, the 2008 is 8 years after 2000. So if I plug that in, y is equal to 1.04 times 1 plus 0.0205 raised to the 8th power. I can plug this straight into my calculator, and I'm going to get approximately 1.22 million people in this town or city, whatever it is, which makes sense because if I'm starting with 1.04 million and I'm increasing each year, 1.22 million is an increase. And then the last problem is kind of the opposite. It says, what's the year that the city's population was 1.3 million? So now they're giving you the y value, 1.3, and that's equal to the initial amount times the growth times the rate, or plus the rate. Now we are solving for that t. So now we're kind of back to this same exact problem we had earlier, where I can't solve that algebraically just yet. So I'm going to graph that. So again, on the Casio, you can put just the formula into your calculator, G-solve. You're going to do an X calculation because you know the Y value is 1.3, and then it will tell you the X value. If you're on a TI, you'll enter in this equation in one, you'll enter in 1.3 in the other, hit enter, find where they intersect, and that will give you the coordinate of T, the years since 2000, and then that population of 1.3. So by graphing again, we're going to get that T is about 11 years. Now you have to be careful on questions like this. 11 years is technically not our answer because it says estimate the year the city's population was. The year wasn't 11. The year was 11 years after 2000. So 11 years after 2000 was 2011. Okay? Be careful like those word problems like that on the quiz. Okay? And then again, I always like to see if this makes sense. If in 2008, my population was 1.22 million, does it make sense that in 2011, it would be 1.3 million? Yes, that would make sense. All right, and then example 3. The amount Y in grams of the radioactive isotope barium, 140, remaining after T days is Y equals A times 0.5 raised to the T over 13 power, where A is the initial amount in grams. Use exponent properties to rewrite this equation into the form Y equals A times 1 plus or minus R raised to the X power. And then, so let's do that first. So the first thing we want to do is rewrite. This is exactly what we did in 8.2. So using my exponent properties, I know that this is really Y equals A times 0.5 to the 1 over 13th power raised to the T power, or the X power, whatever you feel more comfortable with. So then in my calculator, doesn't matter what kind of calculator you have, you can type in 0.5 raised to the 1/13th power, and you'll get a decimal. That's approximately 0.948. So right here, we can see that this is going to be a decay, right? This is a decay model. And so we want to rewrite it as 1 minus some rate. So this is 1 minus 0.052. So that means now I know that not only is it decaying after so many days, but it's decaying at a rate of 5.2%. Okay, and that's the question we needed to answer. What percent of the barium 140 decays each day? 5.2%. Okay, so the question also gave us part of the answer because it decayed. All right. So as you can see, we can talk about these exponential growth models in terms of something of value, like for a car. We can talk about it in terms of population. We can talk about it in terms of, chemical reactions or elements and stuff like that. We can also talk real life applications of exponential growth and decay is bacteria and infection. How fast does a virus spread, or how fast does a disease grow, or how quickly does it dissolve, or something like that. So that comes into half-life and double growth. And so we're going to give you those two models. Obviously, half-life would be a decay. That base is less than 1. And double growth is when you're growing in double each day or each week or each whatever your time frame is. And so obviously that's showing growth because your base is bigger than 1. It's 2. So we have an example of each of those. We have a half-life and we have a double growth. So let's go here. It says the half-life of a radioactive element is 20 days. So I already know that for this problem, I'm going to be using this first model of half-life. So, if you start with 1,000 grams, how many grams would remain after 1 year? So I want to plug in the information I know and solve for what I want. The half-life equation says A sub T. Well, that's just saying the amount after a certain amount of time. So like kind of like your ending amount, or the amount after a certain check-in, or if you want to call it that. So that's at A sub T. So that's actually what we're solving for in this problem. A sub T is equal to A sub 0 is your initial amount. So think of that as like your lowercase a. Your initial amount is you're starting with 1,000 grams times a half. That never changes if you're talking about half-life, which we are here. And then it's raised to the t divided by h power. Well, t is the amount of time that you're talking about. So in this question is how many grams would remain after a year. So t is the 1 year divided by h. H is the half-life. It is the actual half-life. So how long does it take to cut in half? And that's 20 days. Now here's where you got to be very careful. When I did this the first time, I did 1 year divided by 20 days. But what's wrong with that? Our units are not the same. Year, days. So instead of converting days into years and getting some random decimal, it'll be easier for us to convert our year to days. 365 days in 1 year divided by 20 days in the half-life. So this sub t right here is also the 365 if you need to replace that to make you kind of understand that a little bit better. So we want to know after 365 days, how many grams are left. Because what we're solving for is this, that's like our y value, we can plug this straight into our calculator. 1,000 times 1/2 raised to the 365 divided by 20th power. I would definitely put in the 1/2 in parentheses, and some of you might even want to raise that exponent and put it in parentheses. It's not necessary if you do it correctly, but you can if you want to. And so you're going to actually get the amount after 365 days is 0.0032 grams. So not even a full gram is left. And as you know, I always like to take a step back and think about it realistically. Does that make sense? Well, yes. If you're starting with 1,000 and I'm talking about half-life every 20 days, that's less than a month. So think about after 20 days, 1,000 is going to go to 500, which is going to go to 250, which is going to go to 125. That's just after 20, 40, 60 days. So think about an entire year. So yes, it makes sense that it drops down to that low of an amount. Okay. And then double growth. So kind of the same concept, almost the exact same formula, the exact same model, except for the base is different. Instead of a half, it's doubling in size every day, every 20 days, every week, every year, whatever. So this example is talking about a bacteria. It says the number of bacteria in a culture is doubling every 4 hours. So that's why we know we're using the double growth. There are initially 30 bacteria in the culture. After approximately how many hours will there be 300 bacteria? So first thing I want to do is set up what I know and plug in who I know. So what's my initial amount? My initial amount is 30. 30 times 2, because I'm using double growth, raised to the what power? Well, we actually want to figure out how many hours it takes, but we know that the double life is 4 hours, so it's going to be t divided by 4, and we know that we're trying to figure out how long does it take to get us to 300. So this is one where you'll have to graph, just like we did the others. So you're solving for t. And so when you do that, you will get, so the regular model, if you want to call it that, would be like y equals 30 times 2 to the t over 4, or x over 4, if you want to say that. Might help you plug it in a little bit better. X over 4. You're solving for x. If you're using a Casio, you can G-solve an x value, or x calculate, type in the y value of 300, and you'll get the x value. If not, if you're using the TI, two separate y equals, one is the equation, one is 300, see where they intersect, and you should get that the amount of hours it takes is about 13.29. So it takes about 13 hours to go from 30 to 300 if it's doubling every 4 hours. Okay. And then we're going to talk about interest. So we're going to talk about money a little bit. So I don't know if any of you are at the age where you have your own savings account or checking account or like a CD or anything like that. But here's where we talk about money and how it grows in interest. So we're going to talk about compound interest, which is definitely a growth model. Interest, you're never going to lose money if something has interest on it. If you deposit some money in the bank and it has any kind of interest, you're just going to gain money over time. It might not be a lot of money, but you're never going to lose money off of what you deposit. I'm talking about like accounts, not stocks or anything like that, okay? So this is obviously a growth model, and we can see that in the model. It says A, which is our final amount, is equal to P, the principal. That's our starting amount. Think of that as your initial amount, times 1 plus, so that's that growth, your R, which is your interest rate, divided by N, the number of times it's compounded in a year, and then all of that being raised to the N times T. So again, N, the number of times it's compounded in that year, and then T is the number of years. So I know this kind of seems overwhelming. So what I want to do is actually show you an example of two different types of compounding to see how they differ. So it says, how does compounding interest work? So let's just pretend that you have $100 and you're going to put it somewhere where it's going to have 10% interest. Now, that's pretty steep in regards to interest. And if you find that at a bank or something like that, please let me know because I want to put some money in there. Okay. So I'm just using these numbers because they're easier to work with, and you'll see the change a lot quicker. So if I were to compound yearly, this means in year 1, I deposit my $100. It's going to grow and gain 10% interest. Well, what's 10% of 100? That's 10. And so then at the end of year 1, I'm going to have $110 in my bank account. So then year 2 rolls around. Now, year 2, my starting amount is $110 plus 10%. Excuse me. What is 10% of 110? Well, that's $11. And so at the end of year 2, I'm going to have $121. And if I do it for year 3, my starting amount in year 3 would be the 121 plus 10% of 121 would be $12.10, making my total at the end of year 3 $133.10. And you could keep going and going and going and get this same process. That's compounded yearly. So now let's look at compounding quarterly. Well, quarterly means 4 times a year, right? So every 3 months is a quarter. That's 4 times a year. So in quarter 1, I'm going to start with my $100. Now here's the trick with compounding quarterly. Because you're compounding every quarter, you're not getting your whole 10% interest. You're getting a quarter of that 10% interest. So I'm going to have my $100 plus a quarter of the 10%. Well, 10% of 100 is $10. So the 10%, which is $10, divided by 4, if I add that to 100, I get $102.50. That's going to start me off in my second quarter. So I take that amount and I take my 10% of that amount and divide by 4. Well, 10% of $102.50 is $10.25 divided by 4, which is going to give me something like $105.06. So then I'm starting with that in quarter 3. So I start with my $105.06, and I'm going to take 10% of that amount, which is $10 and about, I'll just put this, even though that would be like 51 cents, but again, divided by 4, and that's going to give me something like $107.69. And here, like I said, we kind of are rounding, so it's nothing is perfect, but You get the idea of what's happening. And then at the end of the quarter, at the beginning of the fourth quarter, we're starting with that $107.69, taking 10% of that, dividing it by 4, adding that together, and I get about $110.38. All of this is year one, okay? So we would do it 4 times every single year. Now look at the end of year one here and look at the end of year one here. Is there a difference? Yes. Which one is a better way of earning interest if you're more concerned with gaining a profit or gaining a lot of money? That's going to be compounding quarterly. I know you're probably thinking, but it's only a 38-cent difference. You're right, but we only deposited $100. If you deposited $500 or $1,000 or $15,000 or $100,000 or something like that, right? It would make a bigger impact over just 1 year compounding quarterly than you would compounding yearly. Okay, so that's kind of the difference on just a basic level. So now let's do a problem, and we're going to use this. We're going to use this model because it's really exactly what we just did in the compounding quarterly one. So it says you were deciding between 2 accounts to deposit $10,000. One of them pays 1.65% annual interest that is compounded daily. The other pays 1.68% annual interest that's compounded quarterly. Which account will yield more after 5 years? So the first thing we want to do is set up our model. So for account one, we have a principal amount. So it's kind of hard to see, but we have a principal amount of $10,000 times 1 plus our rate. Our annual interest rate for account 1 was 0.0165. So remember, when I give it to you in a percent, if you're putting it into the model, that rate needs to be a decimal. When you see it in the problem as a decimal and you write your answer as a percentage, you should know how to differentiate between the two and convert between the two. So that's your annual rate divided by the number of times it's compounded in a year. Well, if this one is compounded daily, there are 365 days in a year. All of this being raised to the n 365 times, let me use parentheses, times t, the number of years. Well, we're concerned with how much we get after 5 years. So I'll put 5 in there, okay? So this can actually go straight into our calculator, no matter what kind of calculator we have. 10,000, open a parenthesis, 1 plus 0.0165 divided by 365, all of that being raised to 365 times 5, and we get a total of $10,859.97. So we gained $859, or pretty much $860 in that year if I compounded daily with that percentage, with that annual interest rate. So then let's check out account 2 and see if it's better or worse, because it's a higher interest rate, but it's compounded quarterly, not daily. So let's see. Account 2. Same initial principal. So that's that starting amount. 1 plus, now the rate, the interest rate is, go away. Okay, now the interest rate is 0.0168 divided by, this one is compounded quarterly, so that's 4 times a year raised to 4 times 5, because again, we're worried about it after 5 years. So into the calculator it goes, and for this one, you get $10,874.38. So after 5 years, which account yields more money? This one does. Account 2. More money. Only about $15 more, but hey, it's more money. And that's free money. You just put in $10,000 and let it sit for 5 years. And you gained about $875. Can't complain about that. And then lastly, we'll talk about, again, still compounding and interest, so talking about money. But this time we're continuously compounding. And the difference here is what our base is. So this was an actual annual rate that was compounded a certain number of times. But if it's continuously compounding, we actually use that base of E, that natural number that we found the estimation of last class. So here's our example. You have $5,000 to invest in an account that earns 1.75 annual interest compounded continuously. How much money will you have in 10 years? And when will you have $7,000 in the account? So we have 2 questions to answer. So the first thing we want to do is write out our model. So our model is A, which is the amount over time, is equal to P, that's that principal, it's the initial amount. Our base is E raised to the annual percentage rate times T, so the amount of time. So we have A equals $5,000 times E to the 0.0175 T. So this is our model. And is a growth or decay model. You should know that it's a growth model for 2 reasons. 1, because money, interest, always growing. You can never lose. But 2, remember when our base is E, we look at the exponent. If the exponent's positive, it's growth. If the exponent's negative, it's decay. So this is a growth model. So the first question is, how much money are you going to have after 10 years? So I replace T with 10. And I plug it into my calculator, and I get $5,956.23. So again, putting in $5,000, letting it sit there for 10 years, I gain almost $1,000. Not so bad. The second question is asking, when will you have $7,000 in the account? So this is when I know my amount, and I want to know after how much time I get to that. So I'm solving for T. So again, this is one that you're going to have to graph. Casio, you can G-solve an X calculation. TI, find the intersection. And when you do that, you will get about 19.23 years. So after about 19 years is when you'll gain like about, that $2,000. Okay, that's it, guys. The last page of your notes we already did in 8.2. I moved it up so today's notes wouldn't be so long. So really nothing different. Your models are the same. It's just depending on what you're talking about. You need to know the vocabulary. So see you later. Start preparing for your quiz.